Okay, so we're going to introduce a few new terms and we're going to plant the seeds that are really going to start to help us understand what this chapter is all about. So it's really helpful to understand these concepts. They're going to make the algebraic stuff we bring up later, it's very easy if you kind of miss the point to just not understand those tools. But if you understand the subtleties of why we're doing what we're doing, it makes the calculus a lot easier to think your way through. So a couple things we want to bring up are about maximums and minimums. So this will lead us up to later in the chapter doing things like optimizing, right? So it makes sense. If you're running a business, you might want to maximize profit, right? You might want to say, how can we run our business in a way where we can make the most amount of profit that we can? Or you may want to minimize costs. Say, okay, how can we change the way we're operating in a way that's going to bring those costs down a little bit, right? So it's pretty easy to see why we would want to maximize or minimize things in general. So we have a couple different types of maxes and mins. We have absolute maximums and absolute minimums. You'll also see these if you look in other textbooks or you hear people talk about it. These are oftentimes also called global maxes and global mins. So it makes sense. An absolute max would be the absolute maximum that you can achieve. A global max is the maximum over the entire function. So they mean the same thing. They just go by different names. So if you hear me accidentally say one or the other, you'll know those are the same. Also, if you watch a video or something about this, then you'll understand it's the same language. So that would be the maximum for everything that your function is defined over, would be an absolute max or an absolute min. We also have what are called local maxes and local mins. So that's a minimum over a small area. So if there's a small area, like an interval that we can put around a point, and inside that interval that contains the point, that function value is the highest function value that occurs over that interval, then that's what we call a local max or a local min. So an example in our picture would be right here. There's this area right here, right, over which this spot right here is the maximum over that area. Now, it's not the maximum for the entire curve because we can see over here we get a higher y value, right? We get a larger maximum. So this area right here, that would be the absolute maximum for the function the way that I have this, where it doesn't go on forever in either directions. We've chopped it off. This would be the absolute maximum. This would be a local maximum. Okay, so that's the difference between those. This would be a local minimum right here. And down here, this would be the absolute minimum because that's the minimum for the entire graph that we have right here. Okay, so for the way we have our function defined as its graph, this is the lowest value you can get. So that would be the absolute minimum. All right, and then this first section is really trying to figure out how can we use calculus to get those values. And this is kind of a lot of what this chapter is about. We're going to investigate how do we find maxes and mins. We're going to investigate how do we figure out where the functions are increasing or decreasing, and how do we figure out where they're concave up or concave down. Those three topics are going to come up constantly as we develop them. There's other subtleties that we'll want to look at too, but those are the kind of the big ideas that we're about to dive into. So we've got our local maxes and our local mins, and we have this theorem called the extreme value theorem. The extreme value theorem says that if you have your function, right, if we have any continuous function over a closed interval domain, then that function has to attain its maximum and minimum value. So there's a few different configurations where this can happen, so we'll go through and investigate that. But if you think about it, yeah, if it contains its endpoints, that means it's on a closed interval, then it's got to attain its maximums if it's continuous. So you could come up with something like this, right? Say 1 over x here, right? That function 1 over x, we could look at an interval here and say, well, it doesn't attain its maximum or minimums, but that's because it's not continuous. So that's what we need for the extreme value theorem. We need a continuous function over the interval that we care about, and then we also need an interval that's closed. We need a closed interval there, okay? So if we go back to our function here, let's zoom in on that. Basically, your strategy for going through and finding those maximum and minimums over that closed interval is you're gonna try out all the possibilities, and then you're gonna test which ones actually work. So that's a lot of what this chapter is about. Is we start to look for clues for where our maximums and minimums may occur, and then we take a closer look at those. So rather than looking at the whole infinite number of points that are on this interval, I'm in fact going to narrow it down to just 4 points. And then when we're dealing with 4 points rather than an infinite number of points, we can start to figure out which ones are absolute maximums, which ones are local maxes, and go through and do all that kind of stuff. So here's another concept we want to take a look at. So here we've got a line here. In fact, it's our tangent line. So you can see right here, this is the tangent line to the curve right at this point, right? So notice the connection. What are we dealing with here? Well, we're dealing with a local maximum, and we are dealing with a horizontal tangent line. So the slope of this tangent line is 0. So it stands to reason, if you think about it, there might be a connection here. And in fact, there is, because we can see, look, at our other local min, there is a connection because we can see at our local min, look, we also get a horizontal tangent line. So it kind of makes sense whenever we've got a nice smooth curve and it gets one of these maximums or minimums over a local area, seems like we would get a tangent line whose slope is 0. We would get a horizontal tangent line. And that's actually true. That's the first thing we're going to start looking for. We're going to call these critical points in just a moment. You're looking for places where your derivative is equal to 0, because a derivative being equal to 0 means a horizontal tangent line. And as we can see in this picture, a horizontal tangent line looks like it's a pretty good indication we may have a local maximum or minimum there. Could be a global max or min, but we won't have any idea about that until we start figuring out if it's even a local max or local min. Okay, now be careful here. So one of the things that we're going to see is that if you have a curve like this and you have a local min there, then the derivative is going to be 0, but the derivative being 0 does not guarantee a local max or a local min. So it's a good sign. It's like an indicator that there's a good chance we have a local max or local min there, but it doesn't guarantee it. And here's an example. Take y equals x cubed, take the derivative, we would get 3x squared, and sure enough, the derivative at 0 would be 0, and we can kind of see that here, right? If we get our tangent line right there. Right? However, clearly we do not have a maximum or minimum at that point. So here's where you can see, oh, if I get a horizontal tangent line, pretty good indicator, I probably have a maximum or minimum there, but it is by no means guaranteed. We're looking at a counterexample right here, right? Not guaranteed at all. Here's another example that gives us a case we have to look out for. Look at the minimum here, right? This is the absolute value function. The minimum is occurring right at the origin, 0, 0. And yet, what would the derivative be here? Would the derivative be 0 like we were getting in the previous examples we were looking at? Nope. The derivative here would be undefined because we have a sharp corner. So this function, the derivative is not even defined at x equals 0. So what have we seen so far? We've seen maxes or mins occurring at a place where the derivative is equal to 0. And we're looking right now at an example where the minimum is not even defined in the derivative. So if you evaluate the derivative of the absolute value, you evaluate it at 0, you get that it's not defined there. So those look like points we really want to be looking out for. Where are my derivatives equal to 0? Where are my derivatives undefined? Or we want to look at where is the derivative undefined and where is the derivative equal to 0. And in fact, those two things are what we call critical points. So our definition for the critical point says a critical number of a function f is a number c on the domain of f such that f prime of c is equal to 0 or f prime of c does not exist, which is basically what we just set up, right? We just looked at, oh, it looks like if you have a local max or min, then either what's going to happen is your derivative is going to be equal to 0 at that point, or your derivative is undefined. Now remember, it doesn't work the other way around. If we get a derivative of 0, that does not guarantee that you have a max or min. So you can't just rush ahead. We still have to investigate. But it's nice that this will kind of take all the maxes or mins for our function, and it narrows it down to just a few possibilities of where those things are occurring. So it's really nice to be able to just check 3, 4, 5 points and see, hey, are these my maximums and minimums, rather than having no idea where these things are occurring. Okay, so let's look at an example here. Here we have the function 3x to the fourth plus 8x cubed minus 48x squared. So it's pretty straightforward to go through and take the derivative of this. It's a polynomial. So remember, we want to pay attention to when things are continuous in calculus. These polynomials are continuous, so we're good with that. Also very easy to take the derivative. You can see we get 12x cubed plus 24x squared minus 96x. So then what I'm going to do is try to factor that derivative, because essentially we want to know, where does the derivative equal 0, or where is the derivative undefined? Polynomials defined everywhere, so we don't have to find the critical points where this function's undefined, because it's not going to be undefined, right? So the only things we have to look for are where the derivative is equal to 0. Now, if you're doing a problem that's a rational function, you got to pay attention to where that denominator is 0, because that's going to tell you where the function is undefined. So we have to throw that in with the critical numbers. Okay. So I've got this thing factored here. So it's 12x times x plus 4 times x minus 2. That's the derivative. What we've got here, if we continue to solve this for being equal to 0, is that f prime of x equals 0 at x equals 0, right? Because of this part right here gives us the x equals 0. This part right here gives us the negative 4. And this part right here gives us the positive 2. So now let's take a look at the graph and see what these numbers represent. So these are our critical numbers. These are the places where the derivative was either equal to 0 or undefined. In this case, they're just all equal to 0. So let's take a look at the graph. Okay, so here's what this function looks like. So what did we get? We got 0, 2, and 4. So we can see right here at 2, looks like we're getting a minimum. Right here at 0, it looks like we're getting a local. So this was a local minimum at x equals 2. We have a local maximum at x equals 0. And then it looks like the local minimum that we're getting at x equals negative 4 is also an absolute minimum. That's the lowest point on this entire function. So we have a minimum here that is, it fits the definition for a local minimum. So technically it's a local minimum, but more importantly, it's an absolute minimum, right? If something's an absolute minimum, you already know it's a local minimum. So we would be more concerned about that. Notice that this function has no absolute maximum. Right? The two end behaviors are that they're going up towards infinity. So you're never going to hit a maximum value. If you keep going out, you're always going to get a little bit higher for a function value. So that's kind of the idea for how you would go through and do this. For a rational function, you also got to figure out where that thing is undefined. So you'd set your denominator equal to 0 and then go from there. So those are the sort of basic ideas of what's going on in this section.